Well, we're not all here, but it's past time to start. So I think we'll go ahead and make good use of your time. Do you have questions before we start anything new? Okay, pretty amazing. I'm going to share the screen because I want to write to you. So here we are on my graphics tablet. And we're following right along in the book. We're starting chapter 3 and page 79. And that means that your readings in the book should take you, this is partially from memory, should take you from page 79, and then the problems start on about page 90. So let's be sure we've read those pages and everything will come together. This is not difficult material. So the general chapter title is Centers of Mass or Measures of Center or something like that. I think I'll just call it centers. And this is going to be review, at least in part, because we've looked at several centers already. So let's make a note. There are several. And the first is the mean. And if we're talking about the mean of a sample, then it gets a symbol X with a bar over it. So that's the mean of a sample. And the definition would be to use sigma notation. I don't know if we've done this before or not, but we're going to do it a lot. So let me write it down and explain what we mean. N is the number of pieces of data. And we're going to symbolize the data as X1 and X2 and X3. And you just keep on going until you get to the last piece of data, which is the nth piece of data. There's no ordering implied here. That is, X1 is not necessarily less than X2. Sometimes we order data and then we'll say these data are ordered and X1 is less than X2. But in this sort of a notation, no, it just means these are the data points. And this sigma notation, this is the uppercase Greek letter sigma, and it indicates addition. So what you do if you see the sigma symbol, you add together everything that comes after the sigma. And the I equal 1 to n is the index on the sigma. And how we operate this is we let I be 1, and we write down X1. And that's everything that's over here. So we let I be 2. And we write down X2, and it's a sigma, so we add. And then we let I be 3, and what do you have here when I is 3? You've got an X3, and you've got to add it. And you just keep doing that until you get up to the top index. So this one tells you when to stop. So when you write down Xn and add that in, you're done. And then what do you have to do? You got to divide by how many pieces of data you have in. I think you know that, but I'm not sure that everybody understood the notation. So we'll be using this notation certainly from time to time. Now, if we're talking about the mean of a population, we use a Greek symbol. We use mu for the mean of a population. And this would be defined, well, it's defined almost identical. I equal 1. And I'm going to put a capital N here, though, instead of the lowercase n, xi over n, where there are n items in the population. So the only difference is if we're calculating the mean of a population, it gets a Greek symbol, mu, and we have to add every piece of data in the population. It's sort of rare that you're going to be able to compute mu, because very often, as we mentioned last week, we talked about this, very often you can't get your hand on every item in the population. Conceptually, it's okay. I know about, what shall the population be? Taxpayers in Guadalupe County. That's a set, and it's a well-defined set, but I can't run around and contact all of them in any reasonable kind of time, at any reasonable kind of cost. And so I would be estimating mu rather than computing mu. Usually, it would be possible that we'd have a population that would be very small, and then I could compute mu. Usually what we're going to be doing is using the statistic x bar to estimate the parameter mu. And that's review, because we've talked about parameters and statistics last week. So just to beat this thing to death, let's just suppose that we've got a data set, and I made these numbers up, 5, 9, 3, 1. Now that data set is ridiculously small. If that's the data set you've got, you don't have enough information to do anything other than to illustrate how we would calculate x bar. And we would calculate x bar as 5 plus 9 plus 3 plus 1 over, how many are there? There are 4 over 4. And these will add to 4, and 5 is 9, and 9 is 18. So 18 over 4 would be 4.5. And that would be x bar. What do we do if we've got large data sets? Well, we hope we have large data sets, because that's where the information lives. It doesn't live in small data sets. What we do if we had large data sets would be to use Minitab. We'd enter the data into Minitab, or we would hope that we had an electronic copy of the data so we don't have to enter it by hand. And then we would ask Minitab to tell us what the mean is. So we're not going to be doing things like this. We're not going to be finding the mean of 4 numbers, but it illustrates how we would find the mean if we had 4,000 numbers. It's just this first step right here, adding up those 4,000 numbers that nobody wants to do. And Minitab is the good and faithful servant that can do that for us. Now, we said that there are several means. And so the second mean we want to look at is the median. And that, by definition, is the value in the middle. Now, we can't talk about the middle without ordering the data. And so we're going to have to take our data and write it such that x1 is less than or equal to x2, less than or equal to x3, less than or equal to n. So now we do have to order the data. So I'm reminding you that to find the median, it's the middle in a set of ordered data. I made up an example here that I think we'll just go ahead and look at. Let me scroll a tad. So just some made up numbers: 6, 9, 1, 18, 15, 3. Let's see, 1, 2, 3, 4, 5, 6. So my n is equal to 6. I'm going to order these. Now order, sometimes we'll say sort, means the same thing. Let's see, I see 1 would be the lowest, and then 3, and then 6, and then 9, and then 15, and then 18. 1, 2, 3, 4, 5, 6. So I've got them all. Now the piece of data in the middle is what we defined as the median. But notice that n is even in this case, in this example. So there isn't a piece of data that stands right in the middle with the same number below as the same number above. What we have is 6 and 9 being in the middle position with 2 numbers below and 2 above. So to find the median in this example, and the median has a symbol, x tilde, this would be a statistic, right? Because I'm computing it from a sample. So the median x tilde I would get by averaging 6 plus 9 over 2, and 6 plus 9 would be 15 over 2. And so the median would be 7.5. And that's what our median would be. If n is even, we're going to have to average the 2 numbers that stand in the middle. Now, if n is odd, it's a little nicer. So let's look at a already ordered set. And let's make it 3, 6, 12, 14, 17. How am I doing here? 3, 4, 5. That's enough. N is odd. So if n is odd, there is a piece right in the middle. And so x tilde would be 12. We can talk about the index of x tilde. Now the index, that's just a pointer that tells us where in our ordered set we go to find x tilde. Useful concept if we've got a very large data set. So the index of x tilde is equal to n plus 1 over 2, where n equals number of pieces of data. So let's see how that works. Let's take our first example, this example right here, where n is even. So we'll say E, G, n was equal to, what was n equal to? 1, 2, 3, 4, 5, 6. N was equal to 6. So n plus 1 over 2 would be 7 over 2 would be 3.5. And this tells me to average x3 and x4 in the ordered data. So in the ordered data, this would be maybe I'll write on top. This would be x1, x2, x3, X4, X5, X6. I'm talking about the ordered data now. And if the index was 3.5, then I would want, see, the index would indicate something right in here, but there is no data point in there. But I would take the one immediately below and immediately above, and I would add those together. Here is where we did it. 6, X3 is 6. So this is X3 plus X4 is 9. 6 plus 9, X4 over 2. Of course, in the second example, where n is even or is odd, so for example, in the case where we had n equal 6 pieces of data, that was this example right here, 1, 2, 3, 4, 5. No, this was 5. Yeah, well, 6 isn't odd anyway, I mean, 6 is not the number we wanted here. So maybe 5. Then the index is still n plus 1 by 2 equal 5 plus 1 by 2 equal 3. So X tilde is X3 from ordered data. And the utility would be, suppose that our data set n is equal to 537. We've got 537 pieces of data. Find the median X tilde. Well, what we have to do is, 1, order the data so that X1 is less than or equal to X2 is less than or equal to, and just keep going, less than or equal to X sub 537. Then the 2 index of X tilde is 537 plus 1 over 2 is 538 over 2 is equal to 269. And so X tilde is X269 in the ordered data, in the ordered data list. And we could do another example where we had, this would be an example where we have an odd number of pieces of data, 537, but it would be easy enough to construct an example where we have an even number of pieces of data. If you were doing this by hand, of course, the tedious part would be ordering these things. But there again, if you've got a big data set, you don't order them by hand. You'll use a machine to order those for you. And Minitab will order a set of data for us in the blink of an eye. The labor part of it would be entering 537 pieces of data into Minitab. We hope that we'll be given a data set electronically so we can pop it in without doing that entry ourselves. In the old days, I have paid people on several occasions to enter big data sets like that for me into the computer. I hope we don't have to do that. All right. So that is the median. And now we'll look at another data set called, another measure of center called the mode. And the mode, we don't use the mode too often. Some people use the mode more than others. It depends, I think, upon the discipline that you're working out of. But the mode is the value with highest frequency. It's the value with the highest frequency. So if I had data that looked like 7, 3, 1, 9, 2, 4, 6, 4, 12, if that was my data set, then the mode would be the piece of data that occurs most often. Well, I'm scanning this now. This is prone to error also, so you do it with me, but 7 occurs once, 3 once, 1 occurs once, 9 once, 2 only once, 4 occurs twice. That's not 64. 6 once and 12 once. And so the mode is equal to 4 because 4 occurs most often. That's all the mode is. It's the value that occurs most often. If we're using large data sets, we're probably going to be looking at, and this is a review from last week, grouping our data. So I made up a real quick example. I didn't write a story for what this data is, but suppose that we've got a data set and we've grouped our data. And when we've grouped our data, our groupings look like this. And I'm using the same notions and notations that we did from last week. The first grouping, or the first bin as we call it, suppose is from 1 to 5. So the smallest piece of information that goes in this bin is 1, and the largest would be 4.999999. 5 would not go in this bin. It would go in the next bin, which would be 5 to 9. Because one of the rules for forming the bins or forming a grouped frequency distribution is that all these bins will be the same width. Well, the width of this is 4, so we want the width of this one to be 4, so 5 to 9. And then let me just save a little bit of time by writing these without talking too much. 9, 13, 13, 17, and 17, 21. So this is the smallest piece of data that goes in the bin. This is the upper limit for the bin, but 5 doesn't go in the bin. 5 goes in the next bin. You know how that works. Now, we didn't talk about this last week. I just forgot. You probably read it though, but it's useful and very usual that we would record the class mark. And the class mark is just the midpoint of the bin. So if this is like 1, 5, then I'd add these two, 1 and 5, 6 divided by 2, and 3 would be right in the middle. So my first class mark would be 3. And my next class mark would be 5, and 9 is 14. And then I would divide by 2, and I would get 7 for my next class mark. Now we said that the width was equal to 4. Notice that what separates the class marks is 4. And what separates the lower class limits is 4. And what separates the upper class limits is 4. So that makes it kind of easy to jot these things down if we're working by hand. Now I could do a 9 plus 13 divided by 2 and get this next number, or I could do a 7 plus 4. And I'd get the same number either way, 15 and 19. So these are my class marks. Now the importance and the intent of the class mark is to give me a value that's typical of the values that are in this bin. Now, if I've made my bin too wide, I may have values in the bin that really are quite different from the class mark. And that would be an example of making your bin too wide. And if I've made my bin too narrow, well, then that's probably going to lead to a whole lot of different bins and not get the kind of simplification of data that we want when we do grouped data or a grouped frequency distribution. The next piece would be the frequency or the count, and I prefer to call it the frequency. Now this is, of course, this is made up again. We don't really have this data set to go through and count these, but when I made this up, I said, okay, well, maybe these are the frequencies. Now we can spiff this up a little bit, kind of making it look like this. And think about these two columns as being our frequency distribution. It would be okay to have this column. Very often, this is what you'll get. What does this frequency distribution in this form tell me? It tells me that in the class that had class mark 3, I had 4 pieces of data. In the class that had class mark 11, I had 15 pieces of data. In the class that had class mark 19, I had 4 pieces of data. So that's what the frequency distribution tells me. And we can see at a glance here that the mode, that's the measure of central tendency or a measure of center, the mode is the class with class mark 11. This is the modal class. Right in here is the modal class, because that's the class that occurs most often. We can also, if we get used to looking at frequency distributions, we can see that the distribution here is kind of symmetrical. It climbs to a high of 15 and then it falls off. And the frequencies are pretty balanced below 15 and above 15. If we have this frequency distribution, it's easy enough to find the mode, but it's also easy enough to find the mean. So if my data is presented as a frequency distribution, I can find the mean by calling these guys, again, we'll call them xi's, and we're getting a lot of mileage out of xi. But if I'm doing a mean from a frequency distribution, the xi will refer to the class mark, and fi will refer to the frequency. So this would be how we would define the mean, and we'll use the same symbol, we'll use x bar. This would be how we would define the mean if our data is given to us as a frequency distribution instead of distinct individual pieces of data that we can look at. Now let's be sure we understand what this means. And typically, when you get to a point where I think you understand that we would be adding this over all the classes here, I'll just put down the number. How many xi's are there? This is x1, x2, x3, x4, x5. So this time, let me just put down a little 5 up here. When I think you understand that, I'll stop writing it just to save a little ink and a little time and a little effort. The xi is the frequency of class mark of class I. Fi is the frequency. So what is this telling me? This is telling me that I need to take x1 times f1. That would be 3 times 4. So 3 times 4. And I'm building the numerator here. It's a summation, so I say plus. I let I be 2, 7 times 8. 7 times 8. You move on. 11 times 15. We move on. 15 times 6. And 19 times 4. So there's the numerator. Now, what is this denominator? What do you think sigma fi stands for? What is it? What's the significance of sigma fi?
Is it the sum of all the frequencies?
Yeah. Renee, what would the sum of the frequencies? That is absolutely correct. What would that be? What's another interpretation of that?
It's like how many times the numbers occurred, like the total number of.
That's right. The sum of the frequencies is how many pieces of data we had. So if I would add this column, the frequencies, I would have sigma. Sigma is prettier than that. Sigma fi would be 4 and 8 would be 12, 24, 20. Let's see, 4 and 8 would be 12, 20, 27, 33, 37. Looks like I got it right. So the denominator would be 37. And not to take your time doing this multiplication and addition, if I think I did that with my calculator when I did it yesterday. 399 is 10.78. And that would be X bar, but computed from a frequency distribution. And sometimes we're given frequency distributions, not the raw data. This is much simpler than a listing of 37 pieces of data, isn't it? The simplification always comes at a price. Look at the second row, and I see that the frequency distribution tells me that 8 pieces of data fell in the box 5 to 9, including 5, not including 9. 8 pieces of data fell in here. But where did they fall? Were they just spread out kind of evenly through here? Or were they mostly down close to 5? Or were they mostly up close to 9? I mean, it could have been 8 5s, couldn't it? And the frequency distribution would look the same as if it was 8 7s in here. So we don't know that. If our classes or our bins are not too wide, it doesn't matter. We'll pay the price of losing that information for the simplicity that we gain. So frequency distributions, if they're constructed correctly, give us the correct interpretation of our data. And after all, that's what we're after. We have to be careful that we don't average averages. We're not allowed to do that. An example, suppose that we've got a club, has 34 members. And these members are 10 men and 24 women. And we get out the scale and we see that the average weight of the men is 186 pounds. And the average weight of the women is 143 pounds. What's the average weight of of members. Can we say that it's 186 plus 143 divided by 2, which by the by is 164.5? Can we say that? Does that work? Okay, Andrew is saying no, but why? Why no?
Guessing.
Well, guessing is
There's a
okay.
50-50 chance.
Yeah, that's true. That's true. That's a characteristic of binary answers. You're going to be right half the time.
I think I might know why.
Jonathan, share with us why.
Well, is this the average weight? Like, is this the average weight of a single person, or of the 10 people in general? Because if this is average of a single person, they need to multiply that average by, if it's 106, if a man's weight is 186 pounds, you need to multiply that average weight of one person by 10, and same with the women, and then add those together and divide it by 34. I think that'll be the most logical thing to do.
That's
or
very
just
good.
separately.
Jonathan. No, that's exactly right. That's exactly right.
Thank you.
That's how we would correct it. Now, and so, I mean, we can see that this is probably not right because why? I'm averaging two things here. So I'm weighing the contribution of the men the same as I weigh the contribution of the women. But there's only 10 men and there are 20 women. Now, if we say the average weight of the men is 186, then 186 is equal to the sum men's weight divided by how many are there? There are 10. So if I would multiply here by 10, I would have the sum of the men's weight as 180 times 10. That's how much the men would weigh if I would add up all their weights. The same for women. The 143 would be add up all 20 women's weight and divide by 20. That's 143, or multiply 143 by 20, and that would be the sum of the weight of all the women. So I'm going to write a big no down here. This is averaging averages. You can't do that. But if we would take 186 times 10, that would be the sum of the weights of all the men, plus 143 times 20, that would be the sum of the weights of all the women. So this sum right here would be the sum of the weights of all the members in the club. If I'd put them on the scales one at a time and add up their weights, this is what I'd get. And how many of them are there? 30, what did we say, 34? Yeah, 34. And so that would be
We're missing 4 members. We only have 30 people on top. We're dividing by 34.
Oh, 10 and 20. Oh, you see, I screwed up the example. I made this up and I didn't do a very good job of it. Actually, what I did was when I made up the numbers, I said 24 women, but I wrote down for you today, I wrote down 20. Yeah, the numbers are all okay now. Thank you for catching that though. So this is 155.65. So be careful. You can't average averages. And you will see if you stay alert, reading newspapers or magazines or listening to people talk or internet sites, you'll see examples where people average averages on a regular basis. You can't do that for the reasons that this little problem illustrates. Can't average the averages. Now, let me think. I'm out of room here, but I'm going to clear this screen because there are just a few more things that we need to say today. I find my cursor, there it is. And we'll clear this screen and zoom back up toward the top. The mid-range is another measure of center that's used occasionally, and the mid-range is the high plus the low divided by 2. The mid-range has this advantage. It's pretty easy. Even if you got a big data set, it's fairly easy to find the high and the low. You add them up and divide by 2 and you got the mid-range. And it's a measure of center, and it can be a pretty good measure, or it can be pretty lousy measure. And the reason it can be so lousy is it's very sensitive to outlying pieces of data called outliers. If I have this for my data set, 1, 3, 5, 9, 9. If that was my data set, then the mid-range would be 9 plus 1 over 2 equal 5. And so that'd say my mid-range should be about there. And that's pretty good, isn't it? But what if I had just one more piece of data? What if I had a data set that was 1, 3, 5, 9, 9, and 86? This is an outlier, an extreme piece of data. But now my mid-range would be 86 plus 1 divided by 2 would be 87 by 2 would be 43.5. Now, is there a sense that you like in which 43.5 is the middle of this data set? Is that what you'd call the middle of that data set? Well, it is if you're measuring by mid-range, but that might not be the most useful measure for center to use if your data set has got an extreme value on the upper end or on the lower end. Let's also look at we'll take this data set and let's look at the mean, which I'll just write as X bar. We can calculate the mean pretty easy. This would be 4 and 5 would be 9, 3 9s would be 27. So this would be 27 over 5 would be 5.4, I think. So that'd be the X bar, and the X tilde would be 5. So see that the mean and the median are pretty close together. They're pretty close together. But come over to this data set and calculate X bar, and X bar would be, and I think it would be worthwhile to use the calculator on this one. X bar would be 27 plus 86. Biddly. 27 plus 86 divided by 1, 2, 3, 4, 5, 6 divided by 6 would be 18.83. And X tilde, let's get the index. Now the index 1, 2, 3, 4, 5. I've got 6 pieces of data, so the index would be 6 plus 1 over 2 would be 3.5. So that means I'm going to have to average. And X tilde would be X3 plus X4 divided by 2 would be X3 would be, this is ordered. So X3 would be 5. and X4 would be 9, divided by 2 would be 7. Wow, this tells us something about measures of central tendency. Here we're looking at X bar, the mean, and the mean is pulled up to 18.83 in this data set. All I did was to add 86. I had this data set and I added 86, and the mean went shooting up toward that big value. But see, the median was hardly affected. I mean, it did go that direction, but not all that much. It didn't go to 18.83. It went from 5 to 7 by the addition of this one piece of data. And so if we're asking about the average, say, income, Seguin, Texas, do you think you want to know about X bar or X tilde, or I'm going to leave the mid-range and the mode out of it. Let's just talk about these two. Which do you think would give you the truest feeling for what the average income is? Average can mean different things. Average is not precise. So what would be the best measure of average? X bar, which is the mean, or X tilde, which is the median?
X tilde.
Why is that Jonathan again? Who is talking?
Andrew.
Andrew, why do you like X tilde?
Because there could be 100 people in Seguin that make $1 million a year, and there could be 10,000 people in Seguin that make less than 30,000. That is.
Well, that's exactly right, Andrew. X bar would be sensitive to those multimillionaires, the few of them that are on the top end, and that would pull the average up. X tilde, on the other hand, is not so affected by the outlying pieces of data, and it gives me a much truer value for what people usually think I mean when I talk about the average income. I used to have, and let me check the time here, 3, and this is a 2-a-week class, so we got an hour and 15 minutes, and so we're doing just fine on time. So I used to have an example that I would do with students, and I would tell this long story about having a backyard industry. I run something out of my garage in the backyard, and I'm on a airplane trip, and somebody sits down next to me and recognizes me and say, "Oh, I know you. You're that white slaver that exploits those people in Seguin, Texas. You pay them next to nothing." And I say, "Well, wait a minute, back off of that. I'm taking 5 people that I employ, and they really have no skills before they come to me. I teach them how to do something, and I pay them a pretty decent wage. Let me show you what I pay them." And so it might be June that makes $12,000 a year, and Wanda that makes 12,500, and Sue that makes 13,000, and Chris makes 13,000, and Jason, you don't need to tell anybody else this, but Jason is my brother-in-law, and he makes 150,000. He's the supervisor out there. So what is the average income for these people that I'm employing? And see, if I knew I was going to do this, I would have done the arithmetic beforehand, but it won't take long to do. So we want 12,000 plus 12,500 plus 130, no, 13,000.
200,500.
Plus 150,000. Now, if I've got all those right, and there are 5 of them, so we'll divide by 5. And I say, you know, I'm paying these people $37,500 on the average. Well, that's not a princely wage, but it's more than minimum wage. So, you know, back off. Be kind to me. I'm really doing something nice for these people. Do you think these people feel like they're being paid $37,500 on the average? Is it true that their average income is $37,500? Yeah, that's true. Well, no, it is true. I mean, here it is. We just added them up, and it's X bar is 37,500. What if we were reporting X tilde instead of X bar? I wrote these so that they're ordered so that we can do this, you know, real quick. X tilde, I've got 1, 2, 3, 4, 5. So the index for X tilde would be 5 plus 1 over 2 would be X3, would be this one right here. So X tilde would be $13,000 a year. Does that average give a truer picture of what is going on in my backyard? I mean, of course it does. So you can see why we have different values for center and how the different values tell us different things. And sometimes one is the most appropriate and sometimes the other is the most appropriate. If you will become sensitive to reading things now, like from the Department of Labor or the Department of Welfare or Housing and Urban Development, and when they're giving averages, they almost always give the median, and they'll state that. But listen for that word now. They're giving you the median values for the same reason that you see in this exercise right here. A few very low values or a few very high values can pull X bar away. But X tilde is much less sensitive to outliers. And if we have a big data set and we have summary data, and if we notice in our summary data that X bar is approximately equal to X tilde, we would know just by looking that there are not serious outliers, or if there are, at least they're symmetrical in that data set. There's about as much on the upper end as there is on the lower end if these two things are close together. But if you've got one end loaded, high end or low end, X bar will move away from X tilde. So that's the thing you can just see at a glance when you look at data. You can go, oh, wait a minute, I know something about this data that you don't know. It's always fun to know something that other people don't know. Have you got any questions for me? All right. I'll be posting problems in the eraser. I can't remember if I've done that yet or not, but if I haven't, I'll do it. Well, I don't know. I'll check. If I haven't, I'll do it right away. If you're having trouble, and occasionally a computer network goes down, a big chunk of the East Coast went down last night. Did you hear about that? It's back up today. It was back up by mid-morning, but nobody really knows exactly why it went down. Anyway, the point is that happens. Let me know if you have trouble uploading your files. And I can open it up to give you an exception if you make a good story and it looks like you deserve an exception. So that won't be automatic, but let me know. I don't know. I think that's probably look for new homework, look for a video. In a couple days, I'll have a new video out for you. Keep reading in your textbook, working problems, and take care of yourselves. You're dismissed.